hardly exists. And so people started desperately looking for stranger oxidants. This is Ken Nielsen proposed iron +6, iron +7. They were looking for ways in which you could get rid of all this organic compounds and not have the GC mass spec detect it. And so they came up with this concept that Martian surface must be self-sterilizing. It must be, you put your finger on the Martian soil and it's so oxidizing you have to withdraw your finger in pain. So that's cool, but science then becomes, I see a lot of young people in the audience. I know you're taught that science is fact and neutral observation and logic and all the rest of it. Well, science is really culture. So if the Martian surface is self-sterilizing, and that's what the GC mass spec told us, there's no reason to bother to look for life on Mars, right? So the Mars program lost funding, the staff was disbanded. The relevant labs at JPL closed in 1977 after the Viking result came in. And of course, this is a crushing blow, especially for a government program, right? You don't close it down. You heard yesterday, or just a few minutes ago from Robert, how, you try to keep these programs going. But instead of looking for Martian life, and why bother, said the despondent scientists, including people like me, NASA hosted workshops, funded proposals, designed instruments, planned missions, all to find this mysterious oxidant that was causing the gas chromatography experiment not to see any organics, even though they're falling to Mars all the time. And missions to search for extant life were then off the table. So, okay, in 1996, something came along that almost changed the culture. And that was, of course, they picked up this rock from Allen Hills in Antarctica. It was a rock from Mars, and it had in it things that sort of looked like cells. And so the despondent scientists could say, well, maybe we can go look for life on Mars because, these found these structures. So what are they saying? I've told you about the metabolism theory of life and the reduced carbon theory of life. Well, this is a different theory of life. This is what we'll call the so-called cell theory of life. There is Theodore Schwann. Maybe you remember his being mentioned in your high school biology class as saying that all life is made of cells. And so for a while, this turned out to be stronger than the reduced carbon theory of life, which was stronger than the metabolism theory of life. You're working with me, right? So here you go. But the cells turned out to be too small. And if you look at them in a different direction, they look like mineral ridges, not cells. And so the NASA Astrobiology Institute, which was founded because Allen Hills, right? The story is that, Bill Clinton went to Dan Golden, head of NASA, says, this Allen Hills cells, are these life or they aren't? And Golden says, I don't know. And then Clinton says, what the hell are we paying you for? So they set up the NASA Astrobiology Institute to do these things. But NASA would not set up an extant life search program because in 1976, they tried that. They think that the public was disappointed and the system went away. So NASA would decide to follow the water or look for habitability or look for ancient life force or study geology. And you heard a whole talk this morning from Jim, which is showing how NASA doesn't look for life, but does everything else, including flying drones. Okay, they're very proud of the drones, but they aren't going to look for life. And that's because of the fact that science and technology is a culture. So in 2000, something else happened that almost changed. And that is really my only contribution to this field. I have no other contribution. We showed that the Viking GC mass spec results, or at least their interpretation, was wrong. The so-called missing organic molecules on Mars is the paper that we published a quarter century ago almost. We showed what happened to the organics on Mars. The GC mass spec could have been sitting on a pile of them and not have seen any of them, okay? And it turns out that, in fact, organics are everywhere on Mars. And so in 2013, NASA's Curiosity rover found evidence of organics. Perseverance detected organics in the Jezero crater, which you heard a little bit about this morning. In the Wildcat Ridge, Perseverance has detected abundant organics. And guess what? We predicted a quarter century ago benzoic acids, and in 2021, they found benzoic acids. And we comment on this on our webpage, www.primordialscoop.org, if you want to learn more about it. But now you got to follow with me the logic. Okay, work with me here. And this is Gil Levin's question, right? So there was a defensible logic before 2000, which was that the Viking metabolism experiment said that Mars perhaps has life, but non-life can also do metabolism, your car, okay? So the GC mass specs came along that proved the absence of organics, and right, but life must have organics. So the GC mass spec also proves that meteoritic organics must be toasted beyond recognition. Therefore, the Martian surface must be self-sterilizing by a mystery oxidant. Thus, the statement Mars lacks organics means that Mars lacks life. Therefore, the metabolism results must have not life explanations. Everybody following the logic here? Right? You were taught this in 8th grade in your science fair projects. Excellent. But now you can't defend that logic, right? Because if the GC mass spec experiments did not prove the absence of organics, in fact, we've had experiments, missions, rovers that have found lots and lots of organics ever since, right? You can't say that the logic holds any longer, that Mars must be self-sterilizing. It isn't. It's a fact. And so Gill keeps asking, okay, great. So now that Benner has shown that GC mass specs did not prove that the Martian organics were missing, why didn't we go back to where we were right before, right? And say, hey, wait a minute. Gil Levin found life, or at least evidence for life on Mars, and then sent a mission to confirm the inference. Well, for 20 years, NASA did not find that logic compelling, okay? And that's why you see Jim talking about basically geology experiments on Mars in his talk this morning. Only in 2019, at a conference in Carlsbad, did NASA next consider looking for extant life. There is the paper. I think my name is in there somewhere, but still NASA says it will not launch a mission to find life. If you want to go find life, it's going to have to be a private mission, a Rocket Lab or a SpaceX or somebody who supported by you folks. So culture is stronger than logic, and I hate to see all these poor students who've been going to now have their careers in science crushed. We really do want you to go into STEM, but you got to remember, 20 years, Gil asked that question. NASA never answered it. It flew drones. It looked for fossils. It looked for water. It looked for everything except life. And in 2021, NASA took a step back. It had actually established a panel to define consensus standards to adjudicate claims that people had found life. And the report contains this opening statement: the Viking gas chromatograph spectrometer further supported a non-biological interpretation of Gil Levin's data. That's in the workshop standard. And our response, of course, is no, it did not. But you got to whimper. I mean, I'm just, you have 20 years of this. You show that the mass spec doesn't do it. You find organics on life, but still the official workshop says that, hey, it showed that there was no life on Mars. So for all the students in the room, we teach that science is about observation, fact, logic, hypothesis testing, and so on. But communities of scientists can hold an idea like a dog holds a bone forever, regardless of any of that. And for those of you who would like to have entertaining books, there's Thomas Kuhn's Structure of Scientific Revolutions, which discusses how this works. A more radical book is from Paul Feyerabend, who points out that science theories come to be accepted not because of their accord with scientific method, but because their supporters make use of any trick, rational, rhetorical, or ribald. This is Paul, in order to advance their cause. This is not his prescription, he says. No, it's just his horrifying realization after observing how science is actually done. Okay, so how are we going to meet the message of this particular conference, which is to search for life with heavy lifts? We clearly have got to do better than this. And so what I'm going to do is I'm going to drag in two new theories, okay? To sell a modern audience on this, we must do better. And there are two other theories in addition to cell theory and metabolism theory. There's evolutionary theory and there's information theory. So life, of course, is a self-sustaining chemical system capable of Darwinian evolution. That's what NASA says. That's hardly operational. And that's one of the reasons why metabolism theory was so useful in 1976. You could do an operation, you could look for it. But, and we got Watson and Crick. There's, of course, the informational molecule that we have on DNA. And everybody agrees, by the way, you have to have informational molecules in order to do Darwinian evolution. And there is sort of the Lego description of what AT and GC looks like in your DNA. But remember, that's teracentric. That's what we have, right? What makes us think that the same DNA is found on Mars, let alone Vulcan? And don't tell me it's because a Vulcan man married a American woman and got a child out of it, because then the DNA had to be well, that would be well, what part of the word fiction don't you understand, right? So that's cool. So, but we are synthetic chemists, so we can make alternative forms of DNA. We can actually see what other kinds of molecules can hold information that can support evolution. And so, we've made a complete Lego set, the complete update of all those holes and prongs to put them together. So not only do we have an AT base pair and a GC base pair, which is how you store information in your evolvable information molecules, but we can make other ones, and we make them in the lab and we ask ourselves, hey, do they work? And the answer is they do. Okay, actually, this happens to be just a 6-letter DNA. There's a double helix crystal structure, right? We have 8-letter DNA. We have 10-letter DNA. They all store information. They all work in evolvable forms. We've made skinny DNA analogs. We've made fat DNA analogs. They all work as long as certain criteria met, which I'll talk about in a minute. But which of these should we seek on Mars? Because we know that they exist because we can make them and they work in the lab, even though we can't necessarily find them out on our planet. Well, the answer is we don't know. Actually, my movie references date me, right? So the question is, who knows that picture and what it's from? Raise your hand. Oh, okay, maybe it doesn't date me so much, right? That's Home Alone. Yes, we don't know which to look for. And if you think about it, that creates a problem if you're going to try to search for life on Mars. But because our search must be agnostic, it must not, we have no opinion about what the informational molecule will look like, but we got to find it. And that's hard to do. So one of the other reasons why it's nice doing all this, what we call synthetic biology, that is making alternative forms of DNA, is it actually allows us to identify the ways in which DNA molecules structure can be different and still support Viking life, which, by the way, cannot mate with Terran life and produce a fertile offspring, who is interested in, what's her name, Uhura, yes, right? No, but to support Darwinian evolution, there are some structural features that informational molecules must have to support evolution. And one of them is it must be an informational biopolymer that has a repeating backbone charge. Now, it can be a negative charge, repeating negative charge. That's what you have in your DNA, repeating phosphate backbones. It could be a repeating positive charge. For all I know, Klingon DNA has a repeating positive charge. But the informational molecule, in order to support Darwinian evolution, has to have a positive charge. That is, the DNA must be a polyelectrolyte. The reason for this, of course, is empirical. We've made lots of molecules that have that repeating charge. They work. We made a lot of molecules that don't have that charge and they don't work. But it ultimately works because it allows the physical properties of the molecules to be constant with changing information. There's another criterion we come along. It's actually not ours. It comes from a man named Erwin Schrödinger. Yes, this is the same Schrödinger who had the cat. Okay, he's the quantum mechanics guy. And he pointed out in 1943, before he even knew the structure of DNA, that the building blocks that hold the information all have to have more or less the same size and shape. So there are two criteria universally for genetic molecules, even on Mars, Vulcan, and Kronos. They must have a repeating backbone charge, and they must have a size uniform building blocks. And so that's kind of great. These two are allowing Jan, who's sitting right there and smiling at me because he doesn't like my jokes. And oh, I'm sorry. I got the web page wrong. Alpha Mars, well, we can go to space. We can't get the name web page right. Okay. But there, and Jan will tell you a little bit more about how the Agnostic Life Finder, ALF, as the acronym is built after lunch. So Sean will show this afternoon. He uses the polyelectrolyte structure to recover or concentrate genetic molecules from very sparse sparse solution. That's very easy. A lot of positive charges, you can move it to the leverage. Negative electrode and so on. And once concentrated, we can examine these to decide whether Schrödinger is happening. So ALF makes operational two universal theories, agnostic to the exact structures of molecules that implement them. One is, of course, the evolutionary theory. The other is information theory. And so the missing motivation, however, is to be motivated for looking at life. You have to go back to the first point that we made. You must think that life arose on Mars, okay? Life, otherwise, you got a problem with motivation. Even if you believe that a polyelectrolyte would be a universal sign of that life. So what makes you think that life started on Mars? Well, I mentioned before, it's because we have the same kind of minerals that we think life started on Earth. So we have to go back to the rocks. But let me show you some paradoxes here. We talk about DNA and RNA. There's the structure. I promise not to put too much chemistry in. Here's RNA. It's sort of like DNA. But RNA is believed to have been the first informational polyelectrolyte that enabled the first Darwinian evolution on Earth, or maybe Mars. To believe this, you've got to come up with some sort of prebiotic chemistry that will assemble this molecule out of earth, air, fire, and water with rocks and a couple things that you can get, including maybe organics that are coming to Earth by meteorites. So let me show you some paradoxes here. So one of them is I put into that RNA molecule bonds that are red. Every one of those red bonds falls apart in water thermodynamically. So it's slow, but it's still unstable thermodynamically. And yet RNA must operate in water. So RNA has to operate in water, but it's unstable in water. That's a paradox, which we've got to resolve. There are others. The R in RNA is ribose. I have given you the structure of ribose as the fourth structure from the left. It's a sugar. Everybody knows that sugars are not terribly stable. If you heat them up in your kitchen, they will turn into caramel. You can actually see some caramel forming as I've heated some of that ribose. And that's because these sugars have a carbon doubly bonded to an oxygen, a C double bond O group. And in fact, in 1996, Stanley Miller, that's the famous Stanley Miller who did the early prebiotic chemistry, said that stability considerations preclude ribose and other carbohydrates from prebiotic chemistry, okay? Ribose and other reagents, sugars, were not components of the first genetic material. Well, that's a problem. If R is not possible, then RNA is not possible, right? And so we turn now, this is why I brought along this nice sample of box, which if you contribute to Jan's program, we'll give you as a free gift, right? It turns out that rocks that contain boron solve this problem. Why? Because boron just loves to bind to adjacent OH groups, like in ribose. And so what we do, this is why the mineral's in the box. And the question now is whether, okay, that's marvelous, okay? So, oops, I'm sorry. How do I go back here? Well, I guess I can't go back. That's how I go back. So there you go. So there is borate now binding to the sugars and stabilizing. And that's why borate mineral is in the box of rocks. So that's cool. So now the next point is that, was borate present on early Earth or early Mars? Now, we've had a long fight with Bob Hazen, who argued that plate tectonics are needed to usefully concentrate borate. The logic, of course, is that Earth lacked plate tectonics, sure. And Mars never had plate tectonics, therefore borate could not have been helped form life on Earth or Mars. But now that's why we have Mars geologists like Jim doing exploration, because ChemCam has found borate on Mars. And by the way, ChemCam has also, well, actually, ribose has already also been found in sugars and meteorites. So we know that these sugars is in fact possible. And so there is this model, which I'm not, of course, I have no intention of even spending a word on the chemistry here, which actually gets you RNA from prebiotic chemistry. One of these includes basalt rocks. And in fact, this is the last point that I will make in this talk, and that is that Mars might actually be a better place to make RNA than on Earth, because not only do you have borate and basalt rocks, but Earth might possibly have been completely submerged by water. If that's the case, all the borate would have been diluted into a global ocean, and that's a problem if you live on a water world. But Mars never had the water inventory of Earth. And so the logic now becomes, if RNA is first, yes or no. Well, if it's no, you got different problems. If it's yes, you need to make RNA prebiotic chemistry. Then you have to decide whether you want to use Benner's stupid chemistry. If the answer is no, you get your own goddamn chemistry. But if the answer is yes, then we need minerals in a desert, and we had those on Earth. Well, if the answer is yes, then life originated on Earth. If the answer is no, we are all Martians. Well, with that, so let me stop there. By the way, we have been very nice to have Bob Bruner, who's been a donor to the foundation, provide us with samples of these rocks. By the way, that's not what's in this particular box, but this provides the missing motivation. Mars had the same mineral species that enabled RNA formation on Earth. And so these are the 5 points I'd like you to remember, that the rocks on Earth that likely gave rise to life on Earth were also present on Mars. Life likely originated on Mars. On Mars, life, like all life, presumably found a way to survive the planetary evolution. We know where to seek Martian microbes. Synthetic biology tells us how to seek Martian microbes. And so the goal now is to try to build the agnostic life finder, which Jan will tell you about after lunch. Well, with that, let me thank you for your attention. Stop. I'll be happy to answer any questions if they let me.
We have time for one question.
Thank you. So from an engineering perspective, then, what specific equipment should we make sure to manifest on future life-searching missions? Which ones give us the highest probability of detection per kilogram and watt that they demand?
Yeah, damn good question. Jan has a whole talk this afternoon on that very point. That was a quick question and a quick answer.
Thank you very much. Appreciate it.
Get your USB. It's right there, isn't it?
Is that yours? Oh, that's... Okay, next, our speaker is going to be Dr. Vandy Varma. She will be speaking virtually about the Mars rover operations and role of autonomy and humans in sample return. Welcome, Dr. Varma.
Hello. Hello. I'm going to go ahead and share my screen and let me know if you have any problems seeing it, or if it's not in presentation mode at your end. I'm going to go ahead and get started, and I will assume the volunteer will let me know in case you can't hear me. So I'm going to talk about, today I'm going to be talking about human and autonomous robot teaming on Mars, and particularly in the context of the Mars 2020 mission. And I know there are a number of talks on the science aspect and the Mars helicopter. So I'm going to be focusing on the Perseverance rover. In general, more focus of this is just talking about how we've really been able to make enormous strides in the autonomous capabilities because of this human robot teaming. And I like to say, on Earth, we are making strides in human robot teaming, but humans had existed on Mars, on Earth actually, for 6 billion years before the first documented robot. And so the system is sort of designed such that robots have had to adapt to it, and it's an inefficient process. Whereas on Mars, it's a planet at the moment inhabited entirely by robots. And it offers, I believe, a tremendous opportunity for us to architect it from the ground up so that we can do this teaming, develop it in a way that is really very, allows us to really go beyond what has been possible in the past. Most of you already know this, but I am going to see if I can move my slide forward. Yeah. So most of you already know the concept of the Mars sample return mission, of which the Perseverance rover is the first step. So Perseverance is collecting and caching sample cores, and we're going to have a subsequent lander land on Mars. And the lander, this is a joint partnership between NASA and the European Space Agency, ESA, has the 7 degree of freedom robotic arm, which is going to reach out and get the sample cores from Perseverance. And then we're going to put them in a canister, launch them, a rocket from Mars for the first time. It's going to rendezvous with an Earth return orbiter and then bring them back to Earth. Because of the great success with Ingenuity, we now have 2 helicopters as a backup option on the Mars sample return mission. And you're seeing here in the illustration, sort of an Ingenuity scale helicopter, but it's got wheels and an arm, and there's 2 of them. And those will be used to collect as a backup the sample cores and bring them to the workspace of the lander so that they can be transmitted. And I'll talk about that a little bit more. So going on to, let's see. Going on to the next slide, the biggest, when we wanted to bring samples back from Mars, scientists got together and said, if you're going to bring the first ever samples, we want to bring them from the most interesting place. And the most interesting place ended up being Jezero. But Jezero has this crater, which has an ancient river delta, which has a very high probability of preserving signs of ancient life. But the crater also has walls that are tens of meters. And so we used for landing in that zone, so we wouldn't land in a hazarded area, autonomous capability called terrain relative navigation. And I was showing this video where as we were landing, we could detect if there were hazards and divert from it. And on the landing day, we actually did encounter a hazard in Jezero and ended up landing, doing a divert. So this is showing the crater, which we diverted from. And as a result, the landing site is on the other side of this hazardous zone. And this was a great opportunity. And so we, after doing the checkouts, doing Ingenuity sort of demonstration of the technology of the helicopter, we started the science campaign and used the opportunity to do a crater flow campaign in the South Zeta area, which was really had a lot of science value. And this image here is showing where the landing site was, and in the white, you're seeing the rover's traverse path, and the white are the locations at which the rover stopped, and the red crosses are the areas in which we have collected samples. Once we were done in South Zeta, the really interesting region, which is why we'd gone to Mars, was the Delta. And so, essentially what science would love and what we want to do for Mars exploration is essentially say, can we just teleport the rover to the Delta now that we're done? Except we were over 5 kilometers away from it with, a pretty large 1-ton rover. And we ended up doing this rapid traverse, which you're seeing all the way across around to get to the delta. This was over 5 kilometers and would typically in past mission have taken, in the order of a year, a little less than a year to get there. Whereas Perseverance was able to do that in 31 days. And that really it sort of broke all kinds of interplanetary records for us to be able to do that. And I'm going to go into a little bit of how that was possible. So why is it challenging to get a lot done on Mars at the moment? It's because of this time delay, which most of you are well familiar with, is that we have to go through the Deep Space Network to talk directly to the rover, and then we collect so much data that it has to come through the Deep Space Network back. On top of that, there's a very limited time in the day to actually drive. So I'm just showing an example from one of our plans. This is just a fraction of it. So on the left, you're seeing all the activities, and along the x-axis, you're seeing a cascading effect of the sorts of things we do. And this is a real plan where in the beginning, you'll wake up and you don't want to wake up too early on Mars because it's very cold and you're going to spend a lot of energy just heating things up. So we wake up on Mars and we would do some remote sensing, and then you would do a drive, but you want to get the drive done before you the pass, where the orbiter will pass over so you can send data back to Earth. So the amount of time we typically have in a day to drive is just a few hours. So in that few hours, humans from Earth, seeing the image of the terrain ahead of them, can actually direct the rover quite well, which is what we've done on previous Mars missions. And if you're driving autonomously, traditionally autonomy was slow. And so we didn't use it much because actually the time to drive is so little that if humans can drive more efficiently, because it was faster for humans to drive, the thinking took so long that we didn't use it as much. So the main goal we were trying to solve is it had to be better. That the capability when you have a human robot team is that the robot needs to be better than what humans can do by low level controlling, sort of like controlling an RC car. So some of the capabilities in Perseverance that have really allowed this leap is, it doesn't treat the rover as anything under its entire footprint as a hazard. It can straddle rocks. It also has an improved search. So it's not just looking at simple arcs, it's looking like at a more complex network of paths. It's also able to predict what slip will occur, not just estimate the slip, but it utilizes that in its navigation. We also made the wheels better. So autonomy is always going to drive in a little less informed way than humans can, because we have all of this meta information right now. And so the wheels were beefier so that we don't have to worry about that. And we had the capability called thinking while driving, so that we're actually doing the processing of whether the path ahead is safe or we're still turning the wheels. For that, we had to take the images very quickly. So increase the field of view so we don't have to slew mechanically the mass to take multiple images, also fast exposure time. And then the really big part was it has have very fast computing. So we do the stereo processing in FPGA and have a second dedicated computer. So the results of this, which you're seeing here, is this on the y-axis, you're seeing the drive distance, and this is cumulative odometry. On the y, you're seeing the sol. So this shows up to about sol 562. But the proportion of driving in the orange, which is autonomous, is significantly greater than some of the other variants where you use partial visual odometry and autonomy, and the bottom blue, which is just directed. This is completely the opposite of prior missions where we would do mostly directed driving. So in that rapid traverse, which is shown in the middle here, highlighted, we did 90% of the driving autonomously, and overall in the mission about 80, which is very significant an improvement. So humans are trusting the autonomy so much more that we're using it more. And this particular area in South Seda, highlighted in yellow, I'm going to show this was where we did a drive over a weekend. And so it shows how we use human directable elements. So even though the robot can do autonomous driving, often what limits these capabilities are because how do we communicate our intent? Humans still have information that's valuable. So on the left, you're seeing how this is the actual drive, actual tools we use for driving the rover on Mars, which is, we have a suggested path, which you're seeing in the magenta as the autonomous, and the cyan is kind of the directed part. And then we have zones, the geometric boxes you're seeing is where to keep in and out of. And we give that as a suggestion to the onboard autonomy. If when it's taking images on Mars, when at that point it knows better than we do on Earth, it can choose to deviate from the path. And on the right, you're seeing the actual path, and it did deviate. And over 3 sols, so we had one uplink to Mars. This was sol 350 to 352. We had a weekend, so we could send the plan on at the beginning and then go home. And over the 3 days, because the duration available each day to drive, the rover drove over 500 kilometers. So this is really allows us to start driving in this way while still being able to communicate where we would like it to go. And this is an image from the second sol, end of the second sol of that drive. It shows you the kind of terrain we were driving in with that autonomous driving. And it does an autonomous turn at the end, because when you're driving autonomously with AutoNav, you may be pointed in different directions, but you need to communicate with the Earth, and it may be low in the horizon. So AutoNav will at the end hunt for a position to communicate, which is what you're seeing in the bottom right. That's from this actual drive, when it was hunting for that comp. Now, this other video is actual images taken by the cameras, which are used to do the autonomous navigation processing. So it's doing stereo really fast. These are the images that you use to drive on sol 200, on sol 360 for 210 meters. So this is the sort of terrain that it's navigating through, determining where the hazards are. And you'll see at a point where there's a set of boulders on the right, and it will divert away from them right here and not drive into that more hazardous terrain. And another thing that we're doing on Mars is using Aegis for autonomously doing science. As we're driving these long distances, what if there was really interesting science targets and we're going to miss them? Because part of what you want to do, even as you're driving, is you're characterizing what we're seeing. So here, this capability allows us to take a wide angle image, which you're seeing, which is the nav cam taken on sol 442. And then autonomously on the board, it will figure out what is the most interesting targets for it to shoot with a laser, where you're seeing the red crosshairs are shooting the laser and then taking telescopic images to return to Earth to say, you know, this was interesting, all without Earth in the loop. And this is another terrain where if you just shot the laser in the blind, you might get not such interesting terrain. But because it was able to take a wide angle image, process it to figure out what's most interesting, shoot the laser, and then take the RMI images, we were able to get really good science, even at the end of a drive without Earth in the loop. So now, you know, we have humans trusting the robots to drive long distances and shoot lasers. So this is really a capabilities at the point where we have reached a level of trust where we know that it's going to return a meaningful science as we're doing this autonomously. And then the last thing I wanted to go into a little bit is that it's very important when you do the autonomous capability for it to be adaptable. I mean, we are going to Mars, and as most of you know, it will surprise us. You know, we're going to a place where no human has been. We have a lot of knowledge about it, but we're still learning. And this shows an example of the very first drill hole we did, where we drilled and there was no core. And we realized that the characteristics of the terrain was such that the entire sample had pulverized. And this is another example where we had an anomaly with the bit carousel. So there is a bit carousel on the front of Perseverance, which is how we collect the cores, transfer it, the robotic arm docks with the bit carousel, and we transfer the sample. And then you're seeing on the bottom, there's a second robotic arm inside Perseverance, which extracts that core and then restores it. Caches it after taking some images and doing some measurements. In the middle, you're seeing a picture where we saw that there were some pebbles. And what had happened was when we were doing that transfer, that core had sort of disintegrated a bit and had deposited pebbles. We were able to work around all of these, but it does result in having to adapt, because we will encounter situations that are unexpected, and you're seeing sort of these rock fragments here. So the approach for what works when we do these human robot teamings is also we send thousands of, so you're seeing this is an example, actual plot up to solve 200 of showing commands we have sent per solve for different activities, the robotic arm, helicopter, sample caching, and mobility by each solve. So we can send, over 1,000 commands to do certain activities, but people don't actually think about all of these commands on a daily basis because that would be very error prone. Here is the tools we use. On the left, you're seeing a much smaller set of directed arguments, which we maybe, deviate the path in this way, or adapt when we're doing coring, we might decide to change the levels which we allow. But in general, it's a much higher level commanding. And at the lower level, we can reconfigure it, but we don't deal with it on a daily basis. So we've designed the system to be very adaptable, and that has helped a lot as well. And so here you're seeing the sorts of measurements we have to do with the robotic arm, where we've got an abrasion patch, because the surface of the targets we look at are highly exposed to the atmosphere, and the most interesting science is underneath. And we need to position instruments like Pixel about 2.55 centimeters above the surface with a 45 kilogram turret at the end of a 2-meter arm. So there's a lot of robotic uncertainty we deal with, and position it in contact with rocks for drilling. And there's a lot of unexpected situations that can happen. This was a recent solve a few weeks ago, where, as you can see, the terrain around changed when we abraded, and it further modified when we drilled an adjacent rock. At the same time, we've been able to, because of the adaptable approach we've used, we've collected 14 cores at this point, and it's gotten to the point where we have a really diverse set of samples and a really exciting cache to return to Earth. And we're at Enchanted Lake and getting ready to consider even deploying those samples at a depot so that we have a backup cache that is available if, say, something were to happen to Perseverance. And then in the inset, you're seeing in the bottom right, Perseverance is going to climb over the delta and continue exploring beyond and continue collecting sample cores. In fact, we've collected duplicate sample cores so that the ones that will be dropping off, Perseverance carries another copy, very similar samples from a contiguous location with the rover. This will, shifting to sample return. So these samples that we're dropping off when the lander lands, these are meant for the helicopter to pick up from this location. So the SRL landing site, the helicopters will fly, pick up the tubes, and bring them back to the lander. So essentially, it's going to fly into a helipad zone close to the tube and then drive, because the helicopter will have wheels, and then pick up these tubes and then fly back to the lander and deposit them. So this is really an exciting phase. And then Perseverance is continuing to carry the samples, and the prime option is that the lander will land at a location where Perseverance will drive close to it, and then the robotic arm on the lander will extract the samples out of Perseverance and put them in the orbital assembly. So I'll end with that, and then take any questions you might have about the mission so far or related to human robot teaming.
Can you hear us now?
Can you hear me now? When will the core samples be tested? Where will the core samples be tested when they're returned? Yeah, so the core samples, when they are returned, it's going to be so exciting even just when the samples are returned. When the samples are returned to Earth, they will be collected and taken to a facility where they're going to be kept in a very clean facility. You know, this is the first time we've brought back essentially alien samples to Earth. So there's a lot of protocol behind how they're handled. But after the initial handling, which might actually be done robotically as well, there are going to be laboratories all over the world that are going to be studying these samples for a very long time. Essentially, you know, even now, samples we brought back from the moon are being studied. So these are samples that are just going to be studied all over for a long time. And then, go ahead.
No. So in a best case scenario, will you retrieve both the primary samples on the rover and the backup ones that are dropped?
At the moment, the plan is to do one or the other, because there is a limitation of how many samples can go into the canister. So the canister itself, you know, at the moment it can carry like 33 samples, and there are more. So the scientists can select which samples they want to carry. But the goal is to land, if Perseverance is still functional at the time, to land really close to Perseverance and collect the samples Perseverance is carrying. And then if it is not functional, then utilize. That's the current plan.
Hello. So in case we have humans on Mars before we do the return mission, will you change the return mission? Because humans can get the course you selected much faster, easier, more of them. So will the mission change if we have humans on Mars?
I think that would be very exciting to have humans. And I think if humans will to get to Mars, I think there's a lot of things for us to think about. And so, you know, that's not currently in the plan, but if they were to get in there, I think that, you know, we would have, you know, between Perseverance, the lander, 2 helicopters, Ingenuity, and the humans. That's like 5 robots and humans up. I think that'd be great. But I think we would think about it differently.
Dr. Verma, one more question, okay?
Hi, thank you for a great presentation. I just wanted to know if the helicopters had to go pick up the samples, how would they do that?
So the helicopters are going to fly to a location, a helipad within proximity of the cores, and then the sample retrieval helicopters have wheels, and they will drive into closer proximity and have a robotic arm to pick up the core and cache it, you know, stow it, and then fly back to the lander. That is one core at a time.
Okay, perfect. I think we're going to be ready for our lunch break. Thank you so much, Doctor.
Thank you.